Okay, so we've considered the energy levels of the harmonic oscillator. So the second thing that is obtained from solving the Schrödinger equation is the wave functions for the harmonic oscillator. And that is what we're going to look at next. So firstly, we're going to look at similarities and differences between the harmonic oscillator description and also the particle in a box system. So if you have a look at the potential energy wells for the two systems, for the particle in a box, we know that the potential energy inside the box is 0 and it goes to infinity inside the walls. For the harmonic oscillator, we have a parabolic potential energy well. So if that is x, the displacement, and inside the well, the total energy is both kinetic and potential energy, whereas in this case the potential energy is 0. In both cases the wells are symmetric around the center of the position, and if the displacement, so that means x, is large enough, the potential energy rises to large values for both of these systems. However, there are some important differences. In the harmonic oscillator, the potential energy is related to the square of x. It doesn't change abruptly to infinity like in the particle in a box system. The wave function goes to 0 more slowly in the harmonic oscillator. Here the wave function goes to 0 immediately. And the relationship between kinetic energy and potential energy is a bit more complex in the harmonic oscillator system. So as a result of that, the curvature of the wave function is also a bit more complex. So what do these wave functions that are the solutions to the Schrödinger equation of the harmonic oscillator look like? Remember, here's the Schrödinger equation. There's our potential energy term for the harmonic oscillator. And if you solve this Schrödinger equation, we've looked at the energies, the wave functions have the following form. Basically, they consist of 3 parts. It's quite a complex function. Firstly, we have n, which is the normalization constant. That is multiplied by a second part, which we call a polynomial in x. And thirdly, there is a bell-shaped Gaussian function. And this is what you need to know. There are 3 components in the wave function for the solution to the harmonic oscillator. Normalization constant, polynomial in x, and a bell-shaped Gaussian function. And we're going to look at each of these components individually. So let's first focus on this bell-shaped Gaussian function. This function has the form e to the minus x squared. And it plays an important role in the wave function. So a question that one can ask is, well, what happens to this function if x becomes very large? And the answer is, when x, which is the displacement of the harmonic oscillator, is large, this function goes to 0. So that's important to know. Now, if you write out the harmonic oscillator wave functions mathematically, this is the form that they take. So the wave function, and each wave function is indicated by the quantum number upsilon as a function of x. There we have the normalization constant for the specific state indicated by upsilon. There we have the polynomial, and there we have the Gaussian function. You'll notice that even though this is a function of x, we have the symbol y in the expression. And y is just a function of x. So if you substitute y with x, you have a function that only contains x. And in this expression of y, you see the symbol alpha, and alpha is related to h bar, the mass of the oscillator, as well as the force constant K of the oscillator. Okay, so we've talked about this. This is just the normalization constant. That is the Gaussian function. What about this part? Well, that is known as a Hermite polynomial. So it's a specific or a special type of mathematical function. And all that you need to know about the Hermite polynomials is that you obtain it from the table. So we have a list of Hermite polynomials depending on the quantum number. So that is actually epsilon, our quantum number. If epsilon is 0, the Hermite polynomial is 1. If epsilon is 1, the Hermite polynomial is 2y, etc. So you just obtain that part from the table. And if you have that information, you can construct any wave function for the harmonic oscillator system. Okay, now we have the general expression for the wave function of the harmonic oscillator. Normalization constant for a specific state given by epsilon. The Hermite polynomial and the Gaussian function. So now we can ask the question, what is the ground state wave function of the harmonic oscillator? So we have the normalization constant, we have the Gaussian function. What we need to get is the Hermite polynomial, and if you go back to the table for the ground state, which would be the lowest quantum number, the Hermite polynomial is just equal to 1. So the Hermite polynomial is equal to 1. So if you were to make that substitution, epsilon is equal to 0, is the normalization constant for 0. That part just becomes 1, and then that remains the same, which is what we have there. And then you can go one step further to replace y if you keep in mind that y is x over alpha, and that will give you that expression. So you can just go and check that. So this is the ground state wave function of the harmonic oscillator. If you look at the probability density of the ground state, here we have the top curve, which is the wave function, which is just that one, and the square of the wave function, which is the bottom curve. So the highest probability is in the middle of our potential energy well. So there we have the highest probability of finding the particle when it's described by the ground state wave function of the harmonic oscillator. What about the first excited state of the harmonic oscillator? Again, let's just write the general expression. Let's see what the Hermite polynomial is for the first excited state, 2y. So there we have the expression where that is the Hermite polynomial for the first excited state, and that you get from the table. Okay, looking at the first excited state, if you plot the wave function, it looks like that. It actually goes negative and positive. The square of the wave function gives you those two peaks, and the highest probability are at those 2 points, the highest probabilities. So there we have the wave function 1 and the square of the wave function 1. and the highest probabilities are where y is about 1 and where y is minus 1. So there and there. But we know that y is equal to x over alpha. So if y is 1, x is alpha. If y is minus 1, x is minus alpha. You can go and check that. So the maximum probability density is at x plus or minus alpha corresponding to y plus or minus 1. So in the same way, one can obtain the wave function for any specific state given by the quantum number epsilon for the harmonic oscillator. Now let's have a look at the role of each of these components of the wave function. Okay, so there we have the full set of wave functions. Firstly, the Gaussian function is very important. Remember we said as x increases, this function goes to 0. If x increases, y increases, because x and y are directly proportional. If y increases, e to the minus y squared goes to 0. So this whole wave function, if that goes to 0, the whole wave function goes to 0. So what is the role of this Gaussian function? It ensures that the wave function goes to 0 as your displacement, which is x, increases. Why is this necessary? Well, you won't find the particle or the spring extended very far from the point of attachment, infinitely far. The wave function has to go to 0 at some point. And that part, the Gaussian function, ensures that the wave function goes to 0. So what is the effect of the mass of the particle as well as the force constant on the wave function? Well, if we look at those equations, we know that y is equal to x over alpha, and alpha is equal to that. So y is equal to x divided by and that can be rewritten as x that becomes a half. 2 divided by 4 is a half. So y is proportional to x mk to the power quarter. But in this exponent we have y squared. So y squared is proportional to x squared mk to the power half. If you square a quarter, you get a half. So there's a direct proportionality between y and mass and force constant. So the larger m, the larger y, and the larger y, the faster this will go to 0. So for a large mass, the wave function will go to 0 quickly, and for a stiffer spring, the same is true, and the wave function will go to 0, which makes sense. If you have a large particle on a spring with a specific force constant versus a small particle, the heavier particle will not oscillate as far as the light particle. And the same for the stiffness of the spring. The stiffer the spring, the smaller will the displacement be compared to a spring that's not as stiff. So the wave function will go to 0 more quickly for a stiff spring or for a larger particle. And that is basically summarized in point 2. And then thirdly, as the quantum number epsilon increases, the wave functions spread over a wider range of x, and that is as a result of the Hermite polynomials. So that is the role of the Hermite polynomials. And you can actually see that if you consider the first 5 wave functions. So if we look at the epsilon equal to 0 wave function versus the 1, which is epsilon equal to 4, you can see that this one starts or spreads over a larger area compared to this one. So that's that area, and this one spreads over a larger area. So the effect of that is, or this is as a result of the Hermite polynomial. So that is the role of the Hermite polynomial. Okay, and this figure summarizes the first 5 wave functions, or the first 5 states, and the number of nodes is equal to the quantum number epsilon. Okay, so you should be able to interpret the wave functions or the components in the wave functions in this way and explain the role of each of these different components. And of course the normalization constant just normalizes the wave function. Okay, what does the probability density for each of these wave functions look like? So this is what we have here. For epsilon equal to 0, 1, 2, 3, 4, and epsilon equal to 20. Now the first thing that we see is what we've just mentioned, that the wave functions spread over a larger range as the quantum number increases. So that range is much bigger than this. Does this make sense in terms of energies? Remember, the higher the quantum number, we've got an energy ladder, quantum number 0, 1, 2, 3, energy increases. And you can imagine that in your oscillator. In a low energy state, the oscillations cover a specific range. What happens when the energy increases? The range covered would increase. So this makes perfect sense, that the range would increase like that. Now what else do you see if you look at the probability densities? For the ground state, the most probable position where the particle would be located is in the middle, so basically in the equilibrium position. And that changes in a very specific way. And we'll see that the densities at the ends, or closer to the turning points, so basically where your oscillator stops and turns, increases as the quantum number increases. And in the middle, the densities or the probabilities decrease. And we can see that clearly for the 20 quantum number. So here we have our turning points. There's a high probability of finding the oscillator at the turning points and much lower probability of finding it in the middle at the equilibrium point compared to what we had for the lower quantum number systems. And this is actually again an example of the correspondence principle. Why? If you think about something oscillating in classical mechanics, the moment it reaches the turning point, it stops for a second. It only has potential energy, no kinetic energy, and it actually spends more time there because it slows down then at the equilibrium position where it's moving very fast, stops, slows down, spends more time there. So your probability of finding the particle at the turning points classically is much higher than finding it in the middle. And we see at high quantum numbers this classical behavior again emerges. So what is this called? Correspondence principle. The next section focuses on the properties of harmonic oscillators, and you can leave this section on expectation values and mean energies. We're not going to go through that. And then lastly, there's a section focusing on tunneling, asking the question, can tunneling take place in an harmonic oscillator? And the answer is yes, although the probability of it happening is much lower than in the case of the particle in a box system. So you can just read through this section. And that basically finishes the discussion of the quantum mechanical description of the harmonic oscillator system.